Okay, let's get started. My name is Peng Hou. I'm a master student of computer science. And today, let's talk about this paper called FineStream, fine-grained window-based stream processing on CPU, GPU integrated architectures. In the last lecture, Professor Hu has introduced what is stream processing. And this paper is talking about a new way for optimizing stream processing based on an integrated CPU GPU architecture. First, I want to talk about the difference in circuit queries between a relational database and data stream. Normally, we know about the structure of our data. The data is structured and limited. And we can create several tables like this and design the relation of these tables. Then we insert data. After that, we can use a circuit to get the data, like this table. We are all familiar with it, right? But when you use this way to to process data stream in a real-time scene, the data is always old when you query it. Now, many companies and researchers need to analyze data in real time. This data always transferred as a stream. Here is the data stream. The different color means different types of data. So for example, when you visit a website or check the stock price, and we can draw a real-time trend chart like this picture. It can help us to make important decisions, and this chart will keep changing over time. So when we use circuit to do this work, the first point is I think is everyone may be familiar with circuit, and the circuit is easy to learn. So if you are coding to do this work, you should learn some new skills. Maybe it will spend you weeks or months, but you totally can learn how to use circuit in a couple hours. And the third is eliminate the programming operations. You can change your circuit statement, not the code. And the circuit is a standard, so we can use many standard ways to improve it. And now let's look at how circuit works. Normally, when we execute a circuit query, it will through several steps, like a syntax check and semantic check and optimize. And the circuit query will pass into several query plans, which is a sequence of steps used to access data. And then the execution engine will dispatch resources to the query plans. In this paper, the author will be co-running the query plans on both CPU and GPU to accelerate the computing process. In this paper, the author focused on integrated CPU GPU architecture. So for GPU, it contains more ALUs than CPU. And ALU is the green rectangular. It's a principal components of CPU and GPU. So in a sense, how many ALUs, how many parallelisms. We all know the CPU is designed for general purpose, so it's more complicated because it's just for parallelism. But GPU is designed for graphics processing. For a 1080p screen, it contains more than 2 million pixels. So GPU should do compute simultaneously if you want the display smoother. So GPU has more ALUs, and GPU always has a lower price for each ALU. And you can see the newly NVIDIA GPU RTX 3080. The price is about $700, and it contains more than 8,000 ALUs. And the newly AMD CPU Threadripper 3990X, the price is almost 4,000, but just have 64 ALUs. Now, most high performance computers have independent CPUs and GPUs. But FineStream in this paper is designed on integrated architecture, and the author did a lot of work to prove integrated architecture has more advantages on streaming processing. You may know about Apple M1. This CPU based on ARM and is an integrated architecture. Now you can see many reports about the high performance. So integrated architecture has many advantages, include CPU and the GPU can share the main memory. For discrete architectures, this stream need to copy from the main memory to GPU memory via PCIe, and then the result need to copy back. So the low bandwidth with PCIe will limit the performance, but integrated architecture can avoid the PCIe transfer cost, and also includes low latency, low price, and energy efficiency. Now let's see how to combine CPU and GPU. Here is a table. The author executes the same circuit on CPU and the GPU independently and gets the performance results. The operator means the execution of query plan. In some operator, the CPU has a better performance like this. The others will be on GPU. This table is more like a model. The FineStream will build a model like this table to decide an operator should be run on CPU or GPU. And let's see this idea in another way. For example, we have 3 operators: join, group by, and aggregation. The join group by on GPU faster than CPU, and the aggregation on CPU is faster than on GPU. So we can combine them to achieve the highest performance. Now let's see how to execute a circuit. Data stream is a sequence of tuples. A tuple is a finite ordered list of elements, and each tuple have a timestamp. The window is a data unit to be processed in a query. The window in stream has 2 features: the window size and the window slide. Operators are minimum processing unit in the window. For example, the selection or group by or join. And the query are a form of the query is a form of data processing. It contains a sequence of operators, at least one operator. So it will split data stream as a window size and convert a sequence of operator as a query and then get the result. Next, let's talk about the computing resource scheduling method. The online profiling model is used to analyze input batches and queries, then feed the information into performance model. And the performance model is used to build models for queries, which either CPUs or GPUs, and the performance information includes time span and bandwidth to assess the operator to dispatch. The dispatcher model assigns stream data to operators with proper processors according to the performance model. And device mapping allows an operator to use one or several cores of the CPU or GPU device. And to summarize, when the engine starts, it first processes several batches using only CPU or GPU independently to get the performance information based on this idea. It builds a performance model for CPU and the GPU, and then after the performance model is built, the dispatcher starts to dispatch based on the performance model. And then let's talk about how to handle parallelism. Here is an example. In A, if we co-run this branch simultaneously, and independent branch can be executed in parallel, then the execution can be partitioned into 3 concurrent tasks. And the performance model will estimate the finish time for each branch. So then use the finish time to label the stage, the stage. Here the stage 1 and stage 2, stage 3. And in B, assume that in stage 1, the required bandwidth is exceeds the limit, but the sum of the required bandwidth of branch 2 and branch 3 is okay. Then we can move the branch 3 append the branch 1 and for better bandwidth. Now let's see the batch pipeline concurrency. In A, you can see the branch partition to 2 phases. The operators in phase 1 and phase 2 need to be mapped into different compute units. So these 2 phases can co-run in pipeline. And in B, shows the execution follow in the pipeline. When FineStream completes the processing for batch 1 in phase 1 and starts to process batch 1 in phase 3 in phase 2, and FineStream can start process batch 2 in phase 1 simultaneously. So phase 1 and phase 2 can co-run because they rely on different compute units. And this method can reduce the time delay. Now let's see how to adjust the dynamic workload. Here is the performance model need to calculate the workload ingestion rate, which means the data arrival rate of the branch. When the workload ingestion rate of branch decreases, they can calculate the reduce ratio and assume the computing resources in that branch can be transferred to another branches. So in a 90% workload after operator OP1 follow to OP2, and 10% OP1 follow to OP3. And in B, part of the computing resource associated with OP2 and shall be assigned to OP3 accordingly. Now let's look at the performance. In this paper, the author used 4 computers. 2 is integrated architecture. The other is a discrete architecture. There are AMD A10 and AMD Ryzen platform in the integrated architecture. In discrete architecture, which is Intel i7 plus GTX 1080 Ti and Intel E5 plus V100. Now let's see the TDP. TDP is the thermal design power. It means the power consumption under the maximum workload. You can see the integrated architecture have much lower TDP than discrete architecture. Here is 95, 65, and the discrete architecture, the TDP is 345, 48, 480. Next, let's see the throughput. Here, Q1 to Q9 is 9 typical circuit queries, and the white bar is a CPU only. The white bar with the strip lines is the GPU only, and the gray bar is Sabre. Sabre is an earlier window-based stream processing engine for discrete architectures, and the black bar is a FineStream. On the A10 platform, compared to Sabre, FineStream achieved a 52% throughput improvement, and on the Ryzen platform, Sabre achieved the Sabre achieved a 56 throughput improvement compared to the single device, and the FineStream is still 40% higher than the Sabre. Let's see the latency of the different queries. The latency is defined as the time query start to end. FineStream has the lowest latency because FineStream assigns the operators to their suitable devices. On the A10, the latency FineStream is 10% lower than that of the best single device, and 36% lower than the latency of the Sabre on Ryzen. It's 2% lower than that of the best single device, and 9% lower than that of Sabre. Next, let's see the price throughput ratio. Here, the white bar is Sabre on RTX 1080 Ti. Gray bar is Sabre on V100, and the white bar with strip lines is FineStream on A10. Black bar is on the Ryzen. So compared to Sabre on the discrete architecture, the price of the 1080 Ti is about 7 times higher than the A10, and the price of the V100 is about 64 times higher than that on the Ryzen. But on average, FineStream better than Sabre by about 10 times, and FineStream is about 1.6 times energy efficient than Sabre. Okay, that's it. If anyone has some questions.